As I said, my name is Greg Richardson. A little bit about me. If you don't know me, I have been part of LabVIEW R&D since 1992. I've worked on all kinds of different parts of LabVIEW, many of which you probably use regularly. Here's a few. The intensity graph and chart was one of my first projects back when I started. I've also worked on a few things that never saw the light of day. So back when the PowerPC chips were all the hype, Microsoft ported Windows to PowerPC. They also ported Windows to the DEC Alpha chip. And hey, LabVIEW had cross-platform code, and we had easy access to create code generators. So I ported LabVIEW to both of these. They never shipped, but it was cool. I also worked on a few things that hit the market and are no longer there. Some of you may remember BridgeView. That eventually turned into the LabVIEW DSC module. The student edition was a stripped down functionality version of LabVIEW for students. We've now long since got rid of that and replaced it with the community edition, which is full featured. A little bit better. And of course, I was the tech lead for the language and compiler for this thing called NXG, but at least some of that code lives on in GWeb right now. I also told Darren this. I felt a little bit called out in his presentation yesterday because some of the things he was talking about were things that I was involved with that were never intended to be public, but somehow are. So I was the person that came up with the word sequence, super secret private special stuff. In our naive state back then, before the internet was what it is today, we thought no one will ever figure this out. That read link info from file method, I also wrote the first version of that. And I absolutely know exactly what causes it to crash, and I have no interest in fixing it. So, what I'm going to talk about today, though, is the compiler. Some of the way the compiler works internally. But it's all internal, so why would you care? Well, a lot of it is, most of us are nerds. We want to know. That curiosity is there. But also, knowing a little bit more about what it's doing behind the scenes can help you optimize your code if you need to. So yeah, understanding what it takes to take that increment node and translate it into the actual machine code to do an increment. Also, you know, even this is a little bit misleading because what I showed you is assembly. That's not the bytes that are going to the processor. So I also want to put a little disclaimer here. The compiler is way more complicated than what I'm going to talk about. Some of the things I talk about are simplified, and there's lots of stuff I'm not going to go over, but it should give you some good insight. So first, I want to go through a little bit of the evolution of the compiler. And to start with that, we'll go with the time when there was no compiler. LabVIEW 1 was a purely interpreted language. When you hit the run button, it actually looked at the diagram, figured out what nodes were there, and executed each one as it went. So performance was not great, but this was LabVIEW 1. You also couldn't move a node after it was wired. If you wanted to move a node, you had to disconnect all the wires, move it, and then reconnect all the wires. So it was early days. LabVIEW 1.1 introduced a concept of inplaceness. We'll talk about this. Go into more depth on this, but inplaceness reduces the memory usage of your application. It wasn't until LabVIEW 2 that they introduced a true compiler. So they put in a code generator, generated 68,000 code for the Mac, and that's also when type propagation started and polymorphism. So yes, in LabVIEW 1, you couldn't wire an array of doubles to a plus. It wasn't until they had type propagation and polymorphism that that was introduced. And I say they because this actually was still before my time. I came in the 2.5 era. 2.5 was a rewrite of the code base to be cross-platform. 2.5 was a release that actually wasn't supposed to exist. It was supposed to be LabVIEW 3, and it was going to be Mac, Windows, and Sun OS. It took too long, and they needed something out in the market. So 2.5 was Windows and Sun OS only, because it didn't have feature parity with LabVIEW 2.2. So they didn't want to put it on the Mac. But they wanted to get it out for the other platforms. So in this era, the code generation became more abstract. We had a layer in there. So we had code generation backends for x86 and for the Sun Spark processor. Also in that era was when constant folding was added. Constant folding is just determining which nodes have all their inputs as constant, and we run that code as we're initializing the execution system or as we're loading the code for the VI rather than when you press the run button. So it only runs once. You can run your VI as many times as you want. It's reusing those values. As we continue to evolve the language, we wanted to have more optimizations, more transforms that happened on your code so we could make it more efficient. So we did some of that through the 5 era. 5 is also when we went multi-threaded. I'll talk more about that later. But doing these transforms kind of directly on the diagram was limiting. This diagram is also your source code. We can't go in and make a bunch of changes to it to make it compile better because we have to save what you wrote. So in LabVIEW 8.0, we introduced DFIR, or the Data Flow Intermediate Representation. This is a lighter weight representation than the full diagram. It doesn't have any layout information. It doesn't do transactions, so it can do undo. So it's a lot easier for us to, make more significant structural changes in this representation before it goes to code generation without impacting your original code. And so there were numerous transforms that were added in this era. Also, through the years, the code gen engines that we have varied. We had to go to ARM and the one that there was another, PowerPC, excuse me, PowerPC processors. So we had to have a code generation engine for PowerPC. So yeah, a little bit more about DFIR. Yeah, it is lighter weight, doesn't have as much overhead, and it mostly mirrors the VI source code because when we first create it, it's a fairly equivalent representation of your diagram. But there are some concepts that only exist in DFIR to allow us to, optimize the code generation. So it actually has more classes than the diagram does. And then, yeah, as I said, it's also isolated from your source persistence. So continue to develop more transforms, and around the 2010 era, we kind of felt like, okay, we need to stop chasing processors. Each time some operating system we wanted to support came up, we had to create, our own backend to generate that code. So around here, we switched to using LLVM. LLVM is an open source project. It stands for Low Level Virtual Machine. It's the code generation engine behind the Clang compiler. It supports a whole bunch of processors, and it also supports like the latest extensions. So we never had to extend our code generator to support SSE and AVX. We just let LLVM provide that for us. LLVM was also how we got to ARM. We never wrote an explicit code generator for ARM. We just used LLVM. Now, this is also near the era when NXG was introduced, and the compiler was completely reused in NXG. NXG created DFIR, and that DFIR went through the same compilation workflow as the normal desktop LabVIEW. And that still exists. The DFIR part of that still exists, but it doesn't use the same compiler as LabVIEW. It has its own code generator that generates Vireo, which was mentioned earlier in the week. So Vireo is our own lightweight execution system that's supposed to be easy to port to different platforms, and that is what runs in JavaScript behind gweb VIs. So same concepts, but this is using a different implementation. Oh, wrong way. So let's talk about some of these transforms. I'm going to start with type propagation, even though it's not truly a transform. Because as I showed, except for in gweb, where it runs in DFIR, type propagation happens in the source model directly. So it's happening directly on your diagram. But this is what determines that, yes, you can wire up a path to OpenVI reference, and that's okay. Or you can wire a string. Or, in recent versions of LabVIEW, you can wire a VI reference into OpenVI reference and open a second reference to the same VI. But if you wire up a double, it says, no, I can't accept that. So all that logic of what types are acceptable and even what type your output is going to be based on your inputs happens during type propagation. That's also where we get what we call structural polymorphism. So yes, you can add a double to a double. You can add an array of doubles to an array of doubles, but you can also add just a single double to an array of doubles, or you can add a single double to a cluster of numerics. And all that logic happens in type prop, so we decide what the output type is going to be. And yeah, here, some of the more interesting cases are you've got an array of int32 with a single double. Well, the output type is neither one of those because it's taking the array part from the int32s, but expanding it to a double because of the other input, so the output type doesn't match either of the inputs. But all that logic's there. Another interesting case of type propagation is we call ephemeral types. This is for nodes that don't really know what their type is going to be yet. Prime example is the uninitialized shift register. An uninitialized shift register, when type propagation starts, has nothing coming in, so it has no clue what the type should be. So it produces an ephemeral type output. In this case, that ephemeral type goes to the plus, and so it's getting an ephemeral type and a double, and knows, well, I just kind of ignore the ephemeral type and say my output's going to be a double. Or in the lower case here, it is deciding to take the integer type. That type then propagates to the right side shift register, and we run it all again. We run the loop a second time. On the second iteration, that shift register is taking the type that it got from the first round and using that. So now it knows, okay, I'm going to be a double, and the plus says, yeah, I'm happy with that. I'm not going to change anything. and we know we're done. There are degenerate cases in this, particularly with build array, where you can end up with every time we try to redo it, it decides to make the array one more dimension. So you have to watch out for that. But most of the time it works really well. I wish sets and maps behaved a little bit better. You basically always have to end up creating the constant to get them to get the right type, but there's still some issues there. So another concept is clumping. Clumping is grouping nodes together that will be executed in one chunk. So it's just kind of chunking up, subdividing your diagram. And one of the key concepts to clumping is whether a node is synchronous or asynchronous. So a synchronous node is going to execute in a finite amount of time every time. You know, an addition is a synchronous node. Finding the min and the max, or searching an array, even though the searching an array will vary based on the length of the array, for any given input, it's going to take the same amount of time every time because it's doing the same thing. Asynchronous nodes have some aspect of non-determinism to it. So if you're reading from a file, we're not in control of how long it takes the operating system to go get those bytes. So we treat that as asynchronous. If you're making a DACMX call, there's probably some point in there where the driver may be waiting on data to come from the card or waiting for a trigger. That's asynchronous. OpenVI reference is, if you're loading a new VI, we don't know how long the load's going to take. That's asynchronous. We want to make sure that anything that is asynchronous has that non-deterministic time, allows other things to go in parallel with it if that data is already available. So we don't want to clump synchronous nodes that don't depend on that into the same clump. So here, if you're reading a string from a file, doing a search array, and then reading some more, we want to separate the two reads. But if we schedule the synchronous nodes before the asynchronous nodes, then they're never really waiting on each, or it won't be that long, so we can just leave that together. We don't have to try to split that out into parallel execution because it's going to be fast enough, it's not going to matter. If you have two asynchronous nodes that don't depend on each other, we'll keep those separate. Another key point to this is checking for abort or cooperative multitasking. So in the days up to LabVIEW 5, LabVIEW was a completely single-threaded application. Everything ran in one thread, and so it was kind of the illusion of parallelism. We were breaking up these clumps and scheduling them kind of intertwined with each other to make it seem like multiple things are happening at once, even though it was all happening in one thread. And a key part of that is checking for what we call breakout. Is, okay, we're executing some code. Should we keep going, or should we stop and let some other piece of code run? So at the end of each clump is this breakout. That's also how we abort. In this case, the search1D array and the second file read are in one clump. The code will never abort between those two nodes because we simply don't have something that checks, have we been aborted? But we always want to abort anytime we wake back up from anything that may have taken a while. If you had to wait for the OS to read a file for half a second, then we'd like to check right after that half a second, should we stop? Of course, then we do something even more fun and start merging clumps back together. Because if you have separate clumps, you have to schedule each one individually. And so that scheduling has a little bit of overhead. We recombine them, but we leave those breakouts in place. So at any point, even though we've merged this back into one clump, there's one kind of execution pointer that's working its way through all these nodes. But there's still points in there where it'll check and say, hey, should I stop? And if the answer is yes, then we save off that execution pointer where we were and go do something else, and it'll get rescheduled later and pick back up where it was and keep going. Another thing that creates what we call asynchronous nodes is nodes that require the UI thread. In Darren's talk yesterday, he said that basically every property node and method on any VI server class runs in the UI thread. Well, all VIs default to running in the standard execution system. So when we get to these nodes, we have to switch execution threads and make the call in the UI. Who remembers, well, I'll use the pointer. We went over this node. What was it? Set control value by index. The main reason that that node is faster than using the value property is because it doesn't require that thread switch. It doesn't run in the UI thread. It can run in any thread, and it avoids that overhead of stopping everything, rescheduling in a different thread, running a little bit, and then rescheduling back to the standard thread. That's the big benefit of that node. And it's also why it is its own node, not just a special property, because again, all VI server properties are hard-coded to run in the UI thread. And yeah, orange call library function nodes, try to avoid them. Make sure your DLL is able to handle multiple threads, and your performance will be a lot better. All right, so a little bit more explicit example of parallelism here. Generic nodes, but this is showing that we've got a flow going across the bottom of multiple nodes, but there's a fork in the data flow out to some other node that is also asynchronous, so it was put in its own clump. When that data is available from the first node, we schedule the second clump and then keep going within our clump. And then when we get to the point of, oh, I need data from that other clump, then we wait and say, okay, I can't continue until that's there. And that may mean that the lower clump is put on a wait queue and kind of unscheduled, and then when that data is available, it is scheduled again and picks back up where it was. So that parallelism can be critical to getting the performance you want, but there are also cases where it actually creates additional overhead and makes the code slightly less efficient. So serializing code is not always bad. It just depends on how much time the operations take. Another concept that I mentioned earlier was inplaceness. So inplaceness is all about deciding which buffers, which memory allocations can be reused. In LabVIEW 1, it didn't exist. Every wire was its own memory allocation, and every node had to take its inputs and do whatever to create the values in the outputs. On the left side here, I'm showing kind of a typical class accessor. that defaults to having the pass-through of the class. Even though it's not modifying it, the class comes in and out. Those are almost always in place. So the memory used by the output of that VI is the same as the memory that was used on the input. There are also cases where we use the same memory even though we're changing it. That's referred to as stomping. I'm stomping on my original value. So here, if you're adding two arrays of doubles, the output is likely going to choose one of the input arrays to reuse that memory, and that's where it's going to put its result. In the absence of other influences, that's typically the top input that gets reused, but that may not be the case, because clumping and inplaceness interact. When we branch a wire, on the left side here, I'm showing two synchronous operations. So they would be in the same clump. And one of them is just reading the value, and the other one's going to modify the value. Well, if we scheduled the one that was going to modify the value first, then we would have to make a copy of the value so that it's still around for the one that wanted to read the original. But if we just schedule the one that wants to read it first, then it can read it, and then the other node is free to modify it without having impact. If for some reason those two nodes are in separate clumps, say for example, the index comes from somewhere else that may be available at a different time than the array, then we're more likely to have to make a copy, because as soon as the array is available, the increment wants to execute and stomp on that value. But if the array index may execute later, it's got to have a copy of that original value. So it may have to make a copy. So again, parallelism is great, but it can cause additional overhead as opposed to running everything in sequence. And this relates to something that most of you know, Stephen Loftus-Mercer, is really espousing of you shouldn't have non-modified pass-through values. And I agree with him to a point. Sometimes that causes extra copies. So here again, you've got a class that's following his model of not having that pass-through output. If you've got a read and a write that are both asynchronous, then they can get scheduled in parallel, and we're going to have to make a copy of that class somewhere so the write can have a copy that it modified separate from what the read is using. If you had the pass-through parameter and wired it through to the write, then LabVIEW knows the read is going to be completely done before the write happens, and we know there's no need to make a copy. So I'm not going to say either one is absolutely right or wrong, but there is an impact.
So on the last slide, us as developers, what can we do to make sure that the right one doesn't happen? When you said if the index is coming from somewhere else and we don't have any guarantee that that's going to come before the array, would putting a synchronize between those two help, where we can guarantee that both get there?
If you put a flat sequence around the index array and pass the array through that flat sequence to go to the increment, then again, the data flow order would be guaranteed, and we would not have to make that copy. Yeah, it's the same concept as this. It's ensuring that data flow order. Sometimes enforcing the ordering reduces memory. Sometimes not enforcing that order allows more parallelism and gets you better throughput. It's a trade-off. That's the other thing I'll say. is we always warn people not to prematurely optimize. Don't assume before you've even run the code that you know exactly what it's going to do. Even the people that wrote the compiler try not to make those assumptions. We're a test and measurement company. Test. Write the code, keep it simple, write the code as simple as you can, and see where you have performance problems. You may find, like Tom and his MIDI keyboard, that actually the simple way is perfectly fine. There's no need to optimize it. And we love to hear those stories of, yeah, the performance was fine. Usually we hear the stories of, no, I'm not meeting my loop times. Was the question?
I was just meaning to say that probably usually you would have an arrow wire taking care of the sequencing here, right?
Quite possibly, yes. Error wires enforce sequencing in a lot of cases. Again, that may not be bad. If you really need the parallelism, then you got to watch out for those error wires because you may be eliminating potential parallelism. One of the reasons we created the merge error node is so that you could break those, get things running in parallel, but still do your error handling properly.
Greg, if you prefer the semantics of that left approach and want to avoid the copy, if you just use the error wire like he pointed out,
yeah,
then the compiler knows not to make a copy because it's...
Yes.
Okay.
Anything that enforces that ordering could actually help inplaceness. Again, less parallelism could hurt throughput. It's case by case.
Oh, it's on the bottom here. Okay. I guess this is maybe gratuitous now that you just said that, but presumably you could also use an an explicit in place element to say, you know, I want the result of this to come out of one versus the other, and basically say, you know, you can be assured you don't need I guess that doesn't work though. Yeah.
Yeah, the in-place element has a little different purpose. A flat sequence, single frame flat sequence is the most common thing for that. But any structure where a value is wired through it is going to enforce that ordering. So let's talk about some of the others in the general class of optimization transforms. So this isn't just us figuring out how to execute your code. It's making your code, you know, faster. We have a transform called dead code elimination. So if there's an output that doesn't go anywhere, and we know that a node doesn't have side effects beyond its outputs, then there's no point in executing it. So here, these tunnels, nothing's wired on the outside. There's no point in indexing that array, creating the array output. And the subtract that's feeding that, if we take away the tunnel, the subtract now has no output. The subtract isn't going to have side effects on its inputs, so there's no point in doing that. So we can simplify this down to, you know, a smaller diagram. This also shows combining those multiple compound arithmetic adds into a single node. That's taking some liberties with some definitions. Doesn't necessarily happen that way, but it illustrates the point. Another one is unreachable code elimination. So on the diagram on the left, there's a constant wired to this case structure. So we know at compile time which case it's going to execute. So we can throw away the other case. It's irrelevant. And once we do that, we see that the output of the generate noise is unused. So in theory, we could throw that away. Now, in reality, we actually can't. That's still going to execute somewhere because we can't tell if a VI has side effects. For nodes, we know whether it has side effects on any machine state or anything external. But for sub-VIs, for the most part, we have to assume that it's going to. So that's likely to still get executed. Another of our optimizations is loop invariant code motion. So if you're doing some calculation inside a loop, but all the inputs to that calculation are actually the same for every iteration of the loop, we can move that calculation outside, do it once, and put less code inside the loop.
Hey, Greg.
Yeah.
Over here. Sorry.
Norm.
In terms of the removing non-executing code and kind of the flat sequence structure tactic to be used for some things, just kind of bound sections of code or in placeness, and something we saw yesterday with the G sugar, I think G sugar. Some of that stuff for like the timing. It's like, okay, well, is LabVIEW going to optimize that out? And is there a better degree of predictability that we can all think about when we're doing certain things where we're like, oh yeah, we're making this clever thing, but the reality is we're kidding ourselves because it technically ran completely in parallel some other clumped time.
Yeah. This is a simplification. Part of my disclaimer at the front. Some things are kind of oversimplified. It's still going to guarantee any data flow ordering of anything that's passing through the structure. But for illustration, we say it goes away. So these optimization transforms become particularly interesting when we start talking about inlining. Our switch to DFIR was also a critical piece to enabling inlining. Inlining is a very obtrusive transform to do on your VI. If we're doing that in your original source code, we're going to have to undo all that and put your source code back somehow. So taking your source, putting it in DFIR, we can make all these changes without having long-term side effects. Just helps our code generation. In this VI, we're showing a call to trim white space that says only trim the start of the string. Trim white space has two case structures in it. Once this is inlined, we now have a constant wired to a case structure. We just went through that. So we've inlined it. We can see, yes, that frame of the first case structure is going to execute, but the frame with the match regular expression in the second case structure is not going to execute. Don't generate the code, get rid of it. Another minor point here, this is showing that the code was inlined within a flat sequence structure. Again, we do guarantee the data flow ordering that is represented by that being a sub-VI, even when it's inlined. But the code executed is just as fast as if that second frame had never been there. Another interesting one is the feedback node. The feedback node was probably one of the first things that was implemented completely as a DFIR transform. The final compiler doesn't actually know about feedback nodes because they all evaporate before they get there. So in this case, that feedback node decomposes into something like this, a single iteration loop that uses first run and the select node to figure out which value to use. So when we introduced this new node, it didn't affect the actual compiler, it only affected this transform that made it go away and turned it into concepts that already existed. Yeah?
Why is that a one iteration for loop instead of a true while loop for an FGV?
I'm not even sure which one it actually does, but for illustration purposes, this works. Another one of these features is the parallel for loop. The parallel for loop decomposes into multiple loops. at one point, there was even talk of a code replication structure, which was just a non-looping version of a parallel for loop, where you could write some code and say, I want 8 instances of this code. It's kind of a degenerate case of the parallel for loop, so we just said use the parallel for loop for that anyway. And even this code is, again, an oversimplification of what it actually is. This is mainly representing the case of having evenly divided chunks. We later supported, it dynamically breaking up the chunks, and that introduces a lot more code. But it's all done for you, so you don't have to worry about it. And you can see here, it's splitting out the array, and it does a lot of work to get the separate values put back together in the right order to represent the auto-indexed output of that loop.
But if you wire in that P, then how does it do it?
So there's configuration on the parallel for loop where you set the max parallelism. That determines how many copies of the code we make. When you configure the P, you can actually cause us to not use all of those. So the code's there, but we may use a smaller number of them. So there's 2 values. There's that max number, and then you can restrict it further using P. Concatenating tunnels is another feature like this. So in this case, it's string. You can think of that as auto-indexing followed by concatenate strings. So they all get put together. For arrays, you can think of it like it's the same as the shift register where you're concatenating each time. Again, this is an oversimplification. This was the first implementation of concatenating arrays. But if you've ever done this, you know that incrementally growing that array each time through the loop can actually be less efficient than growing it in larger chunks and filling it in. So the actual transform now does that. It grows the output array in chunks and keeps track of how many elements it's written into it.
Why cannot it pre-allocate just 10 in this particular case right away?
We just didn't implement that as a feature. It could be done, but it's not implemented that way. And then conditional indexing is the same thing. It's just that appending within a case structure.
But if you initialized you put an initializer pre-allocate it, right? If you initialize
Yes.
10.
Yeah. And then you'd use the index array to override it. We also support this on while loops where we don't know the number of iterations. There may be a stop terminal on your for loop, so it may stop early. So we still have to keep track of how many have we written to know where to truncate it when the loop is over. Okay, so that's what I wanted to go through. Yeah, the conclusion is we've done a lot of work so that you don't have to nitpick your diagrams to make them performant. Again, we love to hear when people say, yeah, I wasn't sure if this was going to be fast enough, but I tried it and it was. There are still ways that when you do run into those performance problems, you can make tweaks to make it a little bit better. And with that, I will say, are there any other questions? Saw Eli's hand a little bit earlier.
I'm just curious for the crowd. The compiler optimization settings in the options dialog, can you comment on any, defaults to 5, any guidance or insights on what changing that does under the hood?
Honestly, I haven't looked at those in so long. I don't feel comfortable saying.
Oh, okay.
I never change those defaults. Yeah, Hunter.
All right, I have 2 questions. One, I want to ask about the non-deterministic nature of compilation. From what I understand, if I build the same project, same binaries 10 times, I don't get the same thing. And number 2, which is kind of related, is on benchmarking. If I want to benchmark a search 1D array versus a map lookup, I make a little VI, I just do that one thing. I may wire in a constant and run it 1,000 times. Does that have any bearing on what's actually going to happen in the context of an application?
Okay, I'm going to go with the second question first. Not necessarily. Yeah. Anytime you take the code out of the context where you're going to use it, those ripple effects of inplaceness and clumping may change. So it may not be quite the same. As much as possible, try to get that instrumentation into your real code. There's, I think, a new library coming out called GSugar that has some helpers that make that easy. Then the first question was non-deterministic compiles. Our compiles actually should be deterministic. That does not mean you're going to get the same bits in your exe file. There are things in the exe file that are non-deterministic, unrelated to the compiled code. And we've tried to eliminate a lot of those, but it is very painful. So we haven't completely done that. But yeah, the actual compiled code should be deterministic. Now, we've also had people comment that, particularly on RT, sometimes they deploy and it works, and sometimes they deploy and it doesn't. And there's obviously a ghost in the machine somewhere, but the compile should be deterministic. Sam?
Now do FPGA. But seriously, like, how much of this applies to FPGA? I mean, like, does FPGA still do decaf, and like, where does it break down?
FPGA uses DFIR, and it has transforms. FPGA has a lot more transforms. FPGA does really funky stuff, and I am not the expert in that. Yeah, the actual code that goes onto the FPGA is very different than like the code for a desktop CPU. All right, one more question.
I had a question, it's kind of extending Hunter's thing. If you really wanted to benchmark something, if you were to put it into a PPL and pre-compile it, would that make the benchmark less context dependent?
Yes, as long as that PPL is how you're using the, going to use it in your deployment, then that should be
okay.
Representative. I'm not allowed to answer another question. Okay, one more.
So one of the big things that I gathered was there's trade-off for speed versus performance. Are there any resources for general rules of thumb where like, hey, we need to optimize for speed, for like tips and tricks, for here's where you'd want to design one way versus another?
It really depends on your application. And it's speed versus like footprint, memory usage. And it just depends on what's important for your use case. Okay, I'll be here all day. So if you still have questions, feel free to find me. But thank you for your time.